Morning, everyone. Let's get things started. Welcome to the next installment of the JKMRC Friday seminar series that take place here in Indooroopilly and online, as is the case today. My name is Katerina, and myself and Karina have the honor of organizing the seminars and introducing the speakers this year. Before we start, on behalf of the University of Queensland and the Sustainable Minerals Institute, we would like to respectfully acknowledge all traditional owners and their custodianship of the lands on which we all meet today. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country. We've recognized their valuable contributions to Australian and global society. So today we are privileged to host our speaker, Professor Martin van Kranendonk. And I have a little bit of a bio, although I'm certain that a lot of people are familiar with Martin. So he was born and trained in Canada. He completed his PhD in 1992 at Queen's University, as I learned earlier this morning. And he undertook a postdoc position at the Geological Survey of Canada for a couple of years. Then Martin moved to Australia as an ARC postdoctoral fellow at the University of Newcastle, where he commenced research on the Pilbara Craton. He then joined the Geological Survey of Western Australia back in 1997, and he worked for a further 15 years until he accepted the position of Professor of Geology at the University of New South Wales in Sydney, where he is today. And as director of the Australian Centre for Astrobiology, Martin is a leading world expert on the early history of the Earth, including the habitats and metabolisms of the earliest traces of life, mechanisms of crust formation, and Archean tectonics. Martin has appeared on numerous television and radio documentaries on early Earth. There are also articles about him in New Scientist, and it's in the lunchroom there, and has been involved in educational outreach programs for school children and the general public. So today's presentation is titled A New Australian Sample Return Mission to Mars in the Search for a Second Genesis. And we are privileged because we're the first ones to hear this presentation. So let's welcome Professor Martin van Kranendonk.
Thanks so much, Katerina. Can everyone hear me all right? Good. So as Katerina said, we're going to have a bit of an exploration of Mars today. And this is really an opportunity to hopefully develop a little bit of interest in something that we're trying to put together over the next few years. And that interest we hope to spark collaboration with both academic and industry partners. And so I'm very proud to show this to you today. We've been involved with the exploration of the search for life on Mars for many years. And I'm going to outline a little bit of that history and then also sort of the rationale for thinking about, well, there's current exploration up on Mars, actually by a number of groups, but we still see that there's a potential for thinking about a new way of doing that. So thank you for the opportunity to speak with you today. And I wish I could be up there in person and have a chat with you guys. So you might wonder why there's all this excitement on Mars. Really, you know, some of the imagery that you get back from the red planet is this pretty dry and dusty place. And to quote the NASA Mars Perseverance mission program scientist, it's mostly basalt. But of course, that's not the whole story. And we now know through the exploration of the surface, both by remote sensing and by active exploration by rovers, that there's more to that story. And so I'm going to paint a little bit of that picture for you today. A lot of that will already be familiar to many of you, but I love this image. This was taken quite a number of years ago. It's a series of stills, but showing a dust devil moving across the surface of Mars. So there's no doubt that it's a pretty dry and inhospitable place at the moment. But of course, that was not always the case. And in fact, Mars has been a planet of interest in the search for life, outside of Earth for a long, long time. And this is from 1887 when telescopes were first being developed and they were able to see some of the features on Mars, although at pretty low resolution. And this is actually a map of Mars's surface. And you can see a few things that actually still have the current names. Here's the giant impact crater, Hellas. Here's the Eredania, which is still the name for a basin. There's Tharsis up here, which is, of course, the large volcanic complex, Argyre. So Mara Austral down through here. There are a lot of names that we still recognize today. So, you know, you have to give your hats off and credit to some of those early descriptions. And the patterns that they've drawn sort of look like rivers and channels and flowing water. And in fact, this led to the idea that there were canals on Mars made by flowing water, because those areas that are shaded dark were actually visibly darker. And so it was thought that those represented, you know, huge waterways. And in fact, we now know that's wrong. That's probably actually large dust storms, dark dust storms that covered the surface as they were looking at it. And so part of this sort of sweeping patterns, of course, the effect, the Coriolis effect that you have from a spinning planet. And so there's the cross section shown here with Wasser, or water, inferred. So that gave, you know, hope that there was a lot, potentially the area for life up through there. And so after that, that sort of got taken a little bit further, and you can see there's a bit more artistic license here with very rectilinear kind of patterns, which maybe reflected the style of art of the day. But the idea was that there was melt from polar caps came down into the central area through these canals, and that actually pointed to an active civilization. We do know that, of course, there is seasonal melting of the polar ice caps. So, you know, again, hats off to them for getting part of that story right, but it's not in the way that they envisaged. And of course, there was the famous face on Mars, and people got all excited about that back in 1976. But of course, with better technologies, that sort of disappeared over time. And this is a much higher resolution image of that same feature. It's just a trick of shadows and light. So you have to be careful about what you observe and look at things in all kinds of different ways. Since that time, of course, there have been the NASA exploration of the Mars surface through a series of rovers, first starting with the Sojourner rover in 1997, successful landing of a man-made instrument on another planetary surface. Here we've got then the Spirit and Opportunity rovers, which landed in 2004 and amazingly continued up until 2018. Or at least the Opportunity rover did. The Spirit rover got stuck in sand at a place that I'm going to talk about a little bit later. And then more recently, of course, the larger Curiosity rover, which is still active, landed in 2012. And it's interesting to see this progression in the size of rovers over time, the complexity and the sophistication. Here's that early Sojourner rover. This is actually a panel that's on the Perseverance rover. Just to show the componentry that NASA has launched to Mars. Here are the Spirit and the Opportunity rovers getting larger. Curiosity was a whole jump step larger. And of course, Perseverance up there now is an extremely sophisticated instrument indeed. So one of the major finds that has come from the Curiosity program was a discovery of organic molecules. And it was interesting that Jen Eigenbro had actually suggested that this could be, you know, a sign of life, but it's far from definitive. In fact, the organic molecules are relatively simple rings, and that can come from a variety of different origins. It can come from activity in the solar system. It can come from radioactive or radiation charged particles that interact with components on the surface. So there's no real strong evidence that this would have come from life, because of course organic molecules are much more complex. And this is what even the simplest kind of sort of biomolecule looks like. So exciting discovery, but still a long way from any sort of strong support for life. The Perseverance rover, as I mentioned, is a really complex scientific instrument. In fact, it's a whole series of different scientific instruments that are packed onto a single carriage. It's powered by a plutonium power pack through the radioactive decay that provides long-term power. And it's not then reliant on solar panels, which can get covered by dust. Of course, it has all the cameras and the analytical equipment in the mast. There's a weather station. There's actually an instrument that has ground penetrating radar and can look at the subsurface textures for up to, I think, about 10 meters depth. And then, of course, a whole series of analytical tools and a sampling component that will take samples through drilling and put those into a tube. And then eventually, the idea is that they will get returned to Earth by subsequent missions. So that we were fortunate enough to be at JPL as it was being constructed. Here it is in 2019. Here they are building the Ingenuity helicopter, which has been such an extraordinary success. And now, of course, it's been on the surface for almost a year. And here's a selfie of the rover at the Delta, where it's doing its exploration. There's a very strong Australian connection to the Perseverance Rover, which I just would like to outline. Ken Williford was the deputy program scientist for Perseverance here. He was trained here in Australia in Clitty Grice's lab and then got the job with JPL to be Ken Farley's deputy. And we had them up in the Pilbara a few years ago, and he brought with us at the time the sampling tube, an example of the design sampling tube that they have for each of the individual samples. And the sample material they're collecting is about the length of this tube. It's about the size of your little finger or a piece of chalk. And the idea is to collect about 40 of those samples, cache them on the surface, and then send subsequent missions to bring those back to Earth. There's the sample container, the holder, where all those samples will be stored. And so quite a sophisticated process, of course. And the idea is from the landing site that Perseverance would then explore the delta and go up to the rim and leave behind a series of caches and then bring those back to a central repository where a subsequent mission could come and pick them up, put them up into Mars orbit, and then a third mission would have to come and bring those back to Earth. So it's quite a long process. They've been evolving that idea, that mission idea, for quite a long time. And now they're talking about, in that second mission, having helicopters to go and pick up those different caches and return them because of the success of Ingenuity, the repeated success. It's had more than 20 flights now and is a consistent and reliable tool. So now, of course, Perseverance, this is from only a little while ago. Perseverance has traversed quite a bit of country from where it first was deposited, and it is now on what's known as the Bacon Strip, this light-colored patch of rocks, which are the fine sediments at the toe of a sedimentary delta. And these thick deposits up through here are the coarser grain clastic sedimentary rocks of the delta deposits. And at the base, they are now starting to explore these finer grain sediments, which are actually one of the key targets in the exploration for life, as I will describe a little bit later. We're not going to go to this link, but I do recommend, if anybody's interested in Mars, a close colleague of mine, Steve Ruff, who was on the Spirit rover science team, has been doing a series of podcasts about Mars and about the Perseverance mission in particular. And he updates that every week. And so all the advances, all the problems, all the technical issues, and various other related topics on Mars. He's a Mars expert. It's really informative. They're short videos. They deal with one or two topics each time. And I do recommend you go and look them up if you're interested in Mars. So the Australian connection, Perseverance launched a couple of years ago, and it has all these, and here's the sky crane view of it landing. It was extremely thrilling. It was really a time of great success and joy for a large part of the community. And we've had Australians involved in the Perseverance mission right from the start. So Abigail Allwood, she was a former Australian Centre of Astrobiology student, and she's the first woman and first Australian to be a science leader on a Mars rover instrument, the Pixel instrument. And then David Flannery is her deputy. He was at JPL for many years and is now at QUT, so just around the corner from you guys. And Adrian Brown, these are all ACA students. Adrian Brown is at NASA headquarters. He's a deputy program scientist with our friend Mitch Schulte at NASA HQ. So, you know, as a nation, we should be pretty proud of our contribution to exploration of space. We, in 2019, had the science teams of both the Perseverance Rover mission and the European Space Agency's Rosalind Franklin mission come out to the Pilbara to look at signs of ancient life preserved in the rocks that are exposed up in the northwest of our country. And for many of them, it was the first time to actually see what they would be searching for on the surface of Mars up in the Pilbara. And we were very fortunate to have them for 5 or 6 days. And for many of them, it was a really exciting opportunity. And one of the moments that I'm kind of proud of is that prior to the trip, the word stromatolite was never mentioned in the search for life on Mars. It was all about biomolecules, but after the trip finished, stromatolites became an absolute target for the exploration up through there. At the same time, we conducted an outreach program with school kids from Port Hedland High, Indigenous students, and a couple of my PhD students came up and did some science activities with them. But they also had a chance to meet the mission scientists of the Perseverance and European space missions, and that was a really exciting program. So yeah, it's great that Australia can be involved at that level and have that engagement. So Perseverance is up at a place called the Jezero Delta. It's in Gale Crater, and it's following NASA's protocol, basically, or if you like, its search strategy to follow the water. And that's, of course, because everywhere there's life on Earth, there is water, or vice versa. And so the rationale is that, with this idea of a habitable zone, that early in Mars's history, it had a warm and wet environment. And there's evidence, extensive evidence now of flowing liquid water on the surface of Mars 3.5–4 billion years ago. And one of those places is this area here in Gale Crater. What you see here is the rim of the crater, sort of arcuate, roughly arcuate. It's part of a much bigger structure. But flowing into that is this meandering channel that drops down and cuts through the crater rim and then debouches a sediment load onto the crater floor with these beautiful multi-channeled deposits, looking just exactly like a delta on Earth. And so this was, visually a very powerful candidate for exploration because it was clearly flowing water. And like I said, at the moment now, Perseverance is just at this southern edge of the delta, which is one of the prime targets for exploration. The evidence for flowing water on Mars and its ancient warmer and wetter climate comes from a variety of different sets of information. Of course, there are large flowing channels on Mars. There's extensive development of clays, which come from water-rock interaction. There are deposits of water-laying sediment. These are sulfates from one of the craters that was explored by Opportunity. And then, of course, there are these beautiful flowing lobate structures that probably, in fact, here come from ice, but still indicate that this was probably water ice and that it had this much more extensive hydrosphere in the past. That's now, of course, evaporated or gone into the subsurface. And one of the first indications of that extensive water-rock interaction was through the discovery of those Martian blueberries. And they are these beautiful little concretions of iron oxides that we can see, again, up in the Pilbara, very similar things coming from really effectively weathering, water-derived weathering. And of course, the size of the system is pretty impressive. Here's the Eredania Basin. The outline of a shoreline is interpreted by Irwin and others. And this is a vast basin that appears to have held water. Because of topographic features that indicate a shoreline, it's a 3 million kilometer squared paleo lake. And it looks like it is the source, the feeder for Madam Vallis, which is the large 800 kilometer long anastomosing river channel that ends up in Gusev Crater, which I'm going to talk about a little bit later. So, very large scale hydrous activity. And so the model that's been produced for early Mars, and just note the time scale here. So this is where planetary formation starts. This has a very compressed geological history because it's a much smaller planet compared to Earth. There's no evidence that it actually ever developed plate tectonics, so it's kind of a single lid planet. But all that evidence points that between 4.2 and really up to about 3.5, there was this quite extensively developed hydrosphere. It was also extremely volcanically active, and potentially those two are linked. More volcanism means more heat being pumped out from the planet. And by about 3 billion years at least, most of that volcanism seems to have died off. There is evidence of more recent activity, but only at a very minor scale. So this is that idea of a hydrosphere being developed. Not sure if there were oceans, but certainly large lakes and a hydrological cycle. Now, a lot of that might be already familiar to you. So Perseverance landed through this incredible entry, landing, and descent mechanism, which I'm sure you've all seen the video of. But if you haven't, we might just take a moment to look at that again. Actually, just with time, we probably won't. But if you want to, you should go onto YouTube and watch the landing. It is quite extraordinary because they had cameras that look upward to the parachute and downward, and you can see the whole sky crane operation. If you haven't seen it, it's definitely worth a couple of minutes of your time to dial in and watch that video. It is actually still thrilling to me to watch it again, to successfully land on the planet's surface. And so this is its location where it landed. You can see there are two different geological units across this beautiful curving boundary. Then there's dust here, and the delta target area is up here about 2 kilometers away. And previous rover missions, that would have taken a very long time to cover that distance. But now with the advanced technology, especially the visual capabilities, they can traverse those kind of distance much more quickly. They've already collected a number of samples in their little cores and are now actually exploring the delta. The mission is always got, various stages, and it's in the prime mission stage still. Secondary mission is then to explore more broadly up the delta and continue up to the rim. There's a picture of when it first landed, looking at the surface of Mars, again, very dry and dusty now, but and you're just seeing the delta deposits here in the distance. That was its original target. So just a little bit about Gale Crater and the fluvial deltaic deposits. We now have that confirmed by images and now, of course, samples, but the visual data was extremely compelling. It was interpreted to be deposited during the warm and wet period of Mars and to represent a long-lived delta. And importantly, it was found by hyperspectral mapping to contain iron magnesium smectite clays, which on Earth can concentrate organic molecules. And this was the prime target for the search for life. And so the fact that they are now close to that delta and actually in those fine sediments at the base means they've reached their primary target. The adjacent unit here, called the floor unit, is interpreted to be a volcanic unit, and it was originally interpreted to be younger than the delta because of what was interpreted to be an on-lap relationship to the delta deposits, these outlying remnants of the delta here, to be an on-lap, especially this raised little lip here. And the idea was that when lava flows come out and they meet an impediment, they actually lap onto it and push up a little bit. So the interpretation was that floor unit was, in fact, younger than the delta, even though most of the appearance is that it would say the delta lies on top of this or has been deposited on top and then eroded back. But that's the story that was being portrayed at the landing site meetings. And they had high-rise imagery, oblique high-rise imagery of the front of the delta, showing these beautiful bed sets. And they were able to identify actually an angular relationship here that was able to show that you had the bottom sets, which is the base, the fine-grained base of these prograding deltas. And that became very exciting in terms of having access to the finer grain material in the toe of the delta. And then critically, they were able to analyze that all this blue area, this area highlighted in blue, is where there was concentrated iron, magnesium, smectite clays. And so the idea was we could access these clays and look for organic molecules and potentially then search for biosignatures by bringing those samples back to Earth. And the idea here really comes from analysis of modern delta systems. Here's a classic sort of delta, the prograding silty clays, and then the bottom sets here. So coarse-grained, medium-grained, fine-grained at the toe of the delta, all the clays. And if you look at the concentration of organic molecules in distance from the head of the delta, you'll see that organics get concentrated into the clays. And this is the primary model that justified going to Jezero to search for life, because all the previous missions were about habitability, about was there water, can we prove it, where's the best place to go? But this mission was to search for evidence of life. And the rationale of bringing the samples back is that, okay, we can fit some pretty fancy instruments onto a rover, but to really determine the complexity of something like an organic biomolecule, you'd have to bring those samples back to Earth because yeah, everybody could complain and wouldn't be able to see the samples themselves. So bring it back to Earth, use the best analytical equipment here, and then go to town on it. So that's the idea. And so the model that was presented, we went to 2 of the landing site workshops and presented some information there. But this is the model that was presented for going to Jezero. And I really appreciate their ability to advertise. Because you'd have to say that there are some interesting components here. I mean, the bottom line is that there was this delta, and here's the 4 set beds, the bottom set beds. That's all based on good geology. But notice there's blue water and that there's green delta. And so, the selling is that, oh my God, this was this incredibly fertile, fully alive place, and that there was oxygen because the water's blue and all the rest of it. I thought, good job. It's very far from reality when you actually talk to them and tried to pin them down to say, so what are you thinking? Is this photosynthetic organic life that you're talking about? And they go, oh, no. It's very primitive. It'd be chemotrophic. It would probably just use the nutrients in the sediment that's floating in the toe of the delta. So this sort of green representation of the coloring here is probably not exactly what even they imagined. And so that's interesting. When you really drill down to think about, target choice and stuff. Anyway, so that was the model that was developed. I've shown you in some of those images the scale. It's about 2 kilometers. And so, yeah, it's a really impressive looking delta, but it's nothing like the big deltas on Earth. So here's the size of the entire Jezero crater. And of course, the delta is just one small part of it. This is compared to the deltas associated with the Nile, the Volga Basin, and of course, the Amazon. So it doesn't have the potential of like concentrating organics that some of the very large river basins where that study of organic concentration was from. And of course, there are problems with looking for organic molecules because they can become degraded over time. If there was evidence of life and organic biomolecules 3.5 billion years ago, and they're at the near surface, they can get significantly affected by degradation over time. Because radiolysis, the incoming solar energy particles, can break down organic molecules to significant depths in the surface. And Perseverance was planning to only sample in drill cores that long. The Rosalind Franklin mission had a drill that would go down to more than a meter to get away from this effects. But of course, it's not been able to launch because of the conflict in the Ukraine. And so that's been put off for a number of years now, which is a shame. The other active breakdown mechanism for organic molecules is that the surface is oxidizing. And so that tends to also strongly break down organic molecules. So, the probability of finding complex molecules left on the surface is pretty small. And I think that science paper by Jen Eigenbrode shows exactly that. They're just small, little, simple organics that have preserved. So the oldest, and the other thing is that, the oldest community accepted biomolecule on Earth is 1.64. Now we have had an atmosphere, so we've been protected from that strong radiolysis, for example, but all the old rocks, even those which have been buried for billions of years, they don't contain demonstrable organic biosignatures. There is organic matter, absolutely, but nothing that uniquely indicates life, or not in the way that we accept it for rocks at 1.64. So just to compare, this is the oldest biomolecule that's been discovered on Earth at 1.64, and this is the organic molecule that's been discovered on Mars. I'm just going to skip over this. There's been a bit of discussion about the age of the units. We certainly brought this up at the landing site workshops. We actually thought that the delta was younger than the floor unit, and the floor unit had been dated in a couple of previous estimates at about 2 billion years. And so it raised the question, was it really that old and during the period of the warm and wet? And furthermore, was it actually as long-lived as people have thought? And if anybody's interested, there are a couple of papers here by Mangold et al. In 2018 and by Sharzad and Kinch in 2018, both presented at the landing site workshops that showed that probably that crater floor unit was significantly younger. And in fact, that if you did a full analysis of the incoming river channels, that they were broken, that there were two different components, and that actually the component that led into Jezero was relatively short and could only support a relatively short-lived deltaic system. Anyway, those arguments got, I think, just absorbed, but it didn't change the way that they went. And in our presentations, we and other groups, raised a couple of concerns about it. And in the end, we thought that the mission going there was potentially risky in terms of a primary mission proposal to search for life, because the possibility of returning organic biomolecules would be extremely low. Finding any really significant concentrations is a bit of a needle in a haystack, even on early Earth, let alone on a planet like Mars. And of course, the idea of following the water is absolutely correct and important. But we felt that in terms of their primary mission objective, this was a risky operation. Hopefully they can prove us wrong. And we really support the adventure that's going on. And we'll learn a lot about Mars anyway. So it's a fantastic mission, no doubt. There is examples actually from NASA of justifications that have turned out to be different than the original sort of ideas. And this stems from the complexity and the difficulty of conducting geological investigations remotely. So Gale Crater, where the Curiosity rover has been exploring for a while, here's the landing ellipse. One of the prime reasons for going to explore Gale Crater, aside from the fact that there are indications, again, of flowing water here, you can see the carved in channel, was that this central peak was thought to be impact-generated rebound. And they'd get a look at the deeper parts of the Mars crust. Of course, that's turned out to be different now, and it's actually just a water lane and windblown pile of sediments, which is fantastically interesting on its own right, but it shows you the difference of when you get there and compared to what you can do by remote sensing. So interesting in terms of our understanding of the differences between what you can see remotely and what you can see on the ground. So we went with a team and we advocated for a landing site to go back to Columbia Hills, where the Spirit rover had undertaken investigations back in the 2000s. And in the end, our site came up number 3. In some cases, we were actually second to Jezero. Our science rationale was actually voted the highest of all of the missions, but it didn't come into top spot. And we think that going back to Columbia Hills actually presents still a really good opportunity for exploration of Mars more broadly and the search for life on Mars. So why an interest in Columbia Hills? So here is a very large crater indeed. And I realize I've forgotten to put on the scale here, but this is, I'm not going to say the distance because I'm going to get it wrong. But it's something on the order of 100 kilometers. It's a large impact crater. And it's at the end of that Madame Vallis that comes in here with the delta deposits. The Columbia Hills are this little triangular piece of outcrop here. And the Spirit rover landed here on the Hesperian lava plains and then traversed across and did some exploration of that area. And what they found were deposits of opaline silica, which have been interpreted as deposits from hot springs by Steve Squires in its original paper in 2008 and in a bunch of studies later. And hot spring deposits are interesting for a number of different reasons if we think about the search for life. There's now a community shift, a paradigm shift in the thinking about the origins of life, from the deep seas to life on getting started on land in hot springs. And we've been just one group that's been involved with this, but there are many different arguments and reasons why it's now thought that life more likely originated on land. There's the water problem, that organic molecules break apart under permanently wet conditions. There's a concentration problem. There's all kinds of issues about deep sea origin of life. And so now the idea is that if life got started on Earth in hot springs, then hot spring deposits elsewhere could be a really interesting target for life. Another major contributing factor is that our studies on the oldest, most convincing evidence of life in the Pilbara at 3.5, those rocks are actually in a hot spring environment. And we have evidence for inhabited hot spring deposits at 3.5 billion years ago, the same age as some of the crust on Mars during its warm and wet period, and very likely the age of the silica hot spring deposits at Columbia Hills. The third main reason is because hot springs are taphonomic, really important elements for preserving evidence of life. And here's just an example from Rotorua. We have the hot spring in the background. You can see it steaming away. And then they harbor very vast communities of microorganisms, diverse communities of microorganisms. So in the orange and the browns here are the living microbial mat, but right down flow, as the mats are growing, they get silicified by the fluids that are coming out of the hot springs. So all of the white silica sinter that you see has now been shown to be actually silicified microbial mat. And so hot springs preserve microbial communities in situ at the time when they're growing. And there have been lots of papers that demonstrate here. Here's a rather ugly looking piece of silica sinter, but when you do detailed analyses, all the green is organic carbon preserved in these microstromatolites known as spicular geyserite. And in places you get actually preserved microbial filaments, which again retain organic matter. And we found evidence not as well preserved as this, but in the rock record back to 3.5 billion years ago. So hot spring deposits can preserve evidence for life. So what did the Spirit rover actually find? Well, it found two really exciting components that we think are worth thinking about for a return sample mission to Mars. The primary feature that was discovered by Spirit are a series of outcrops of opaline silica. These are actual rocks, but they have a very unusual and distinctive texture. They're not finely laminated like a lot of silica sinter, but they have this nodular appearance and they have a digitate kind of structure. They have these finger-like protrusions sticking out of them. As well, in the same vicinity across this area of Columbia Hills are these sulfate-rich soils, which are found in areas where there's high steam fluid passing through from hot springs and sulfurous sort of hot spring environments. And so, like I said, Steve Squires originally suggested that these could have been hot spring deposits, and it was based on the spectral analysis of the silica. Here's the home plate silica with two very distinctive troughs. And then you can see that in Opal A from laboratory experiments, which is just hydrous silica, they have exactly the same profile. And it's different from microquartz, where you can see that those troughs are offset. And so it was based on this that they identified opal. And Steve Ruff has done further analysis of this and found that there's actually a slight halite coating on these samples from home plate as well. More interestingly, those nodular silica deposits on Mars, here with a geological hammer superimposed for scale, actually have been found to have one-to-one correlates in hot spring deposits in the most Mars-like environments on Earth, from the Atacama Desert at 3,000 meters elevation, high UV radiation, high evaporation rates. And you can see that here's an outflow channel from a hot spring. And instead of forming laminated silica sinter, like is very, very common, you get these beautiful digitate nodules. And the hammer here for scale shows that they are at 1-to-1 correlation. And, Steve's done some extra work in this, of course, and here's a detail of one of those digitate structures from Mars. And here are some of those digitate structures from a place called El Tatio. And the exciting thing is, of course, when you look at those structures in more detail, if you break off one of those, you'll see that they are actually microstromatolites. They have fine internal scale lamination, upward convex laminations. And when you probe more deeply and break off some of those and look internally, they are packed with microfossils. And in fact, the suggestion is that those digitate structures are microbially mediated, that they would not form without the activity of microbes. And so the question is, are we looking at a biosignature on Mars? And here's a more detailed look at the fine scale lamination. And this is actually trapped filamentous cyanobacteria preserved here, still with the cyanin pigment. And they're in life array during the daytime and then nighttime array through here. And you can see how silica just encapsulates these microorganisms as they're growing. So this was published in a paper in 2016. And then we've done a bit more detailed analysis of the distribution of these features. So in the dashed line here is the outline of where the silica deposits were found around this feature called home plate, which is about 80 meters in diameter. Home plate is a series of volcaniclastic rocks, and that's an inward dipping centrocline, actually, that the rocks are dipping up to 15 degrees. And what's beautiful is that the Spirit rover spent a winter here, and it took some very high resolution images, which you can go onto Google Mars and see for yourself. These are those images. And the opaline silica units occur at a boundary between a unit known as a buff-colored platy unit and an overlying lapilli-bearing volcaniclastic succession. And here you can see that those units are actually dipping into the ground. You can reconstruct the geology by looking at these high-resolution images, and this had never been done by the Spirit team. So what we were able to show is that here's again that buff-colored platy unit. Here, the digitate nodule silica deposits. There's the overlying lapilli unit. And there are some nodules in other places, but those can be explained by deflation. We can see fragments of the lapilli-bearing unit coming downhill, and we can see components of the nodular silicate isolated here and also just caused by deflation. These are all erosional products down the slope. But these actually, their original stratigraphic position can be used to map them and make a geological map. And when you actually trace the occurrences of the silica deposits and the dips, they outline folded bedding of a single unit that's been folded around this home plate area. And so that's very exciting. We've been able to identify a stratigraphic relationship and put them into a stratigraphic context within that area. And the best thing is we know exactly where those samples are because Spirit has already found them for us. And so we're very excited to think then about developing a mission to go and pick those samples up and bring them back to Earth. And I'm cross-appointed at the University of Okayama in Japan, which is the lab that's actually analyzed. It's a geochemistry laboratory that's analyzing the return sample material from the Hayabusa 2 mission that Japan launched a few years ago. They have an extraordinary facility built by my colleague Eizo Nakamura, who's the fellow here in purple. And he's good friends with a very senior engineer in JAXA. And we brought them to New Zealand to see this idea of in situ silicification of these microbial mats. And they got very excited when they started to understand the full rationale of what we were talking about and the reason for going and collecting this. And so Inatani-san here, the senior chief engineer who designed the heat shield capsule for the return of the material from the Ryugu asteroid, he tasked a series of 4 junior engineers led by Naoya Ozaki to develop a mission plan. And they are all JAXA engineers working at university positions. And we developed a mission concept, which is to be extremely light and nimble. And it's to bring back a payload of only a maximum of 100 grams of 10 different samples across a variety of different lithology, but aimed principally at bringing back samples of these digitate silica nodules from home plate. And if you stay very light and nimble, and we don't need any fancy analytical instruments on a rover on Mars, all we need is an imaging and collecting rover that can identify the samples that have already been found, put them into a sampling cache, and bring them back. And the architecture that our colleagues have developed can actually do all of that in a single launch. And the idea is that with a single launch, it has two components that can be deployed after escape from Earth's gravity. A sample retriever satellite would be put into a stationary orbit in deep space at the Sun-Mars L1 Lagrangian point, and it basically just stays there until it becomes reactivated. The second component is an entry, descent, and landing system that would be deployed for direct entry onto the surface of Mars near Columbia Hills. And that will consist of fetch sample collecting components, either drones or rovers. It will have an ascent rocket, which is actually only going to be about 1.4 meters high. Because the payload's so small, we would insert the samples into a little CubeSat, and that can be brought off the surface of Mars with a relatively small ascent vehicle and the sample container within that CubeSat. That then ascent vehicle, after sample collection, would then rendezvous with the sample collection retrieving satellite, transfer the CubeSat into that satellite. That would then be deployed into a swing by of Mars for return to Earth, deploy the samples back to our science team. And so this is actually a mission that costs significantly less than current missions because it's light and nimble, because it utilizes a lot of existing technologies. That ascent vehicle exists. Japan is famous for having relatively small rockets, highly efficient with electric motors. And you can just buy a launch with a Falcon 9 rocket for about $70 million, develop the hardware. The preliminary costing is for something like less than $1 billion. We could develop this mission and have samples back by the early 2030s, potentially. And so this is something I'm deeply excited about. And we're just at the very starting stages. We just about have our mission architecture document completed, and we're going to start hitting the road and looking for industry partners. It's interesting that our JAXA engineers have actually suggested that we do a mission like this as a startup outside of the official space agencies, because their bureaucracy and their timeframes are so extremely long. JAXA already has primary missions to go to the moon of one of the moons of Mars, to Phobos, to collect sample material there, to learn about the history of solar system origin and evolution. And NASA, of course, has many missions lined up, as you would be aware. And so now with the excitement of, a space race 2, with the energy that's being put in by Elon Musk and Jeff Bezos, and the interest now in Australia with its own space agency and a lot of activity now in the space sector, we are excited to think about the possibility of developing this on our own, hopefully in collaboration and conjunction with those space agencies, but led by the consortium that we are calling the Life Springs mission, obviously based on that idea of life in hot springs. And so I'm really excited to be able to present this to you. This is kind of a way of starting the process. I'm going to start devoting a significant amount of my time to this project, and hope we find some interest. Just as an example of what we're talking about and why we think something like this might be successful, here's one of the digitate structures from El Tatio. This is a micro CT scan showing the very complex style of layering that you can see internally. And the key thing here is the scale. So this is 2 millimeters by 2 millimeters. And so our objective is to get 1 cubic centimeter of the digitate opaline silica nodules from 3 different localities, texturally slightly distinct, and then a sample of the sulfate soils, some of the volcanic rocks, and some of the different units that are in that close vicinity, so that we can learn also about the origin and evolution of Mars, about its hydrosphere, and about its geological history, and bring those samples back to Earth and do all the analyses here. So that's a broad outline. If anybody's interested to learn more, or to get in touch with me, or to be part of this project, please let me know. I don't know what happened there, but I'd like to thank my team and the opportunity presented today to give this talk to you. So thank you very much, and I'm happy to take any questions.
I'm certain you will be able to see any questions come through online. So yes, anyone online, please feel free to type them in, but we will also read them out. Do we have any questions from the audience?
So Graham, Gordon, of course, has one about quarantine. So listen, that's absolutely one of the key components of any mission, is to have both a planetary protection officer, or at least a planetary protection program, and then really deal with concerns about quarantine for material coming in. The fact that we're not looking for current life, we're looking for ancient life, 3.5 billion years old or more, can go some way towards that. But of course, quarantine is a big issue, and we have close colleagues at NASA that we're going to be in contact with. And in fact, I've got a PhD student looking at exogeoconservation who will be involved in this process as well. A robotic laboratory, well, that's the exciting thing about the Okayama University lab, is that they have actually developed all of their analytical tools to be accessible remotely. They did that because of COVID. Once COVID hit and they were not allowed to leave their homes, ESO applied for more than $1 million funding from the Japanese government to make all of their analytical tools accessible remotely. And that includes like a SIMS ion microprobe. They've got 4 Neptunes. They just have a whole, and they've got this Orbitrap machine for analyzing organic materials. They've now automated all of that systematics. So of course, if we are dealing with Mars materials, it'll have to be a next level up. But of course, and that's a community thing. So absolutely, we will be engaged with that kind of discussion.
Thanks, Martin. Rick Valenta here. That was a really fascinating talk. Just super exciting stuff. But what made me think of when you say, I'm really excited about this and we might even get it by 2032, it made me think of all the people who followed the Game of Thrones, not the series, but the books as they came out, at 10-year intervals, and maintained excitement for all that period. But actually my question was around sort of near surface hydrothermal systems that produce sinters and opal and silica, and then some of the various things that you described. And I guess my experience with them is mainly looking for gold in them and silver and so on. I guess the two things that came to mind as you were describing this is that some of the opal and silica is clearly associated with, when you described it as being associated with mats and so on, it makes a lot of sense. But there are other areas within the systems I've worked on where you get opal and silica that's clearly replacement of another lithology that doesn't have that origin. And the other thing is there's usually a really clear kind of plumbing system that you can see, and the sort of alteration units are not strata, they're not following stratigraphy, they're transgressive to stratigraphy. And I'm just interested to know if you're seeing that sort of level of complexity there, because the what you described at home plate looked like something that was very much bound by the stratigraphy.
Yeah, really, really good points. Of course, hydrothermal systems are extraordinarily complex, and we're working together with Kathy Campbell, who's one of the world's leading experts on hot spring systems down in New Zealand. So 2 parts to that. One is that, the digitate silica nodules are part of a stratobound sequence, so they are surface deposits. And interestingly, that buff-colored platy unit has sulfate alteration, whereas the overlying lapilla unit does not. And so that's part of an interesting association that we think may help support that idea of a hot spring system. Now, it's relatively thin, and we're not trying to fool anybody by saying this is a long-lived hydrothermal system and the origin of life on Mars. But if life only just got started, and you think about the sort of first and last place that life might be able to get a foothold, hot spring environments are really the ones. In terms of a third-dimensional view, the amount of tilting of those strata there is only on the order of 10 or 15 degrees, and we don't really have any three-dimensional profile down into the subsurface to look at, so we can't answer that question. But there is an area up in the northwest corner of home plate that was not visited by Spirit, but photographs were taken, and it looks a little bit like a triangular-shaped and potentially even a mound environment, but we don't know. It has also those spectral features of opaline silica. Of course, there's more work that we could do if we were able to go back there in terms of mapping it out and understanding better potential flow directions, channels, etc. That was not looked at by the Spirit team. And in fact, I don't think they really understood what they were looking at when they discovered those units or had the understanding that it was part of a stratigraphic sequence. So we've done sort of, like I said, a bit of a reanalysis of the surface geology, and I think we've been able to sort of advance that science, but there are many key pieces that are missing. But in terms of our understandings of modern systems, we're very confident that it's not residual silica. There's no indications that it's replacement. So all of the images that are available, you never see, little domains where you can see laminae of like you find in the buff-colored platy unit. There's no indications in the spectral signatures of residual aluminum or other things if it was replacing an original material. And in fact, one of the first discoveries of that opaline silica is when one of Spirit's wheels locked up and it was dragged across one of the outcrops and it broke a sample and flipped it over. And the top of the sample has that sort of digitate nodular texture, but the base of it is more of a granular kind of material with porosity. And that is also very characteristic of what you find in the modern centers from El Tatio. And so there are surprisingly consistent sets of observations that suggest that this is a surface deposit from a hot spring.
Fascinating. Thank you, Anna. One more question in the audience?
Yeah, thanks so much, Martin. That was a fascinating talk. My name's Anna. You've reminded me why my first degree was in earth science and the excitement that I got from doing that. I've moved a long way from that now. I do a lot of integrated research. At the end of your talk, you were talking about JAXA suggesting that perhaps an expedition could be mounted outside the remit or the purview, if you like, of the space agencies. I was wondering, I'd really value your insight into whether the space race can get out of control here. I mean, you've obviously got a scientific inquiry mission in mind, but I'm just wondering whether you see a risk of moving outside the framework of, I suppose, people who've been, groups that have been established to pursue scientific inquiry to a more commercial exploration of space.
Absolutely. I think that any startup venture is inherently initially potentially more risky. And we'd be foolish not to admit that that's the case. On the other hand, commercial development of space activities is developing extremely rapidly, and technologies are becoming available to people from all kinds of backgrounds in all kinds of different countries. And so we think we're probably positioned at the right time to be able to take advantage of that and utilize that towards a mission. Now, you could argue that the space agencies have the quality control and dedicated engineering required to successfully deploy a mission of such complexity. And there is absolutely an issue around that. Again, that's not something we shy away from. We want to work in collaboration with the existing space agencies. Having said that, I think what Elon Musk has shown is that they have actually leapfrogged the technology available at NASA. They're now the ones providing them with the launches for many of their missions. And so, we're in that milieu. We are, only just starting, and we need to get absolutely the big players in space on board for this because it is complex. And, I'm hopeful that with our connections to NASA, we may be able to get them to help with the EDL. And with JAXA, we've got existing technologies that is actually in the public domain. So you're absolutely right that this is a big aspirational project. And maybe I'm completely naive to think that there's even a chance of doing it. I don't know. But one thing we are excited about is that we think we have a very high quality science and engineering rationale for pursuing this. And although we haven't actually really gotten started in terms of trying to promote this and develop partnerships, we've already had expressions of interest from significant spacefaring companies and from organizations that are interested to be involved. And if we think about sort of Australia's position, it's great that we've contributed to existing missions and we have this sort of long-standing involvement. But there's also the idea that it could be time that we step up and start thinking about taking a lead on these things with our expertise. And so that's kind of where we are. And we are absolutely trying to build a consensus group towards this. The rationale is now agreed to, the architecture is agreed to. Like I said, we're at the very, very final stages of getting our overview document set so that we can start looking for partnerships. And so obviously, project integration is a big thing. There are many big components to this. And obviously, 2032, 2033 is aspirational. And listen, we've just got to try.
Thank you, Martin. This is fantastic. Of course, we have just one more comment.
It's a very quick comment. It's a wonderful talk. Thank you very much for a fascinating talk. I think we're very privileged to be living at a time when the technology allows us to do these things. It's wonderful. Just to add a small historical context to your point about the number of Australians that are involved in these projects. Of course, the Gale Crater, where Spirit is operating, is named after Walter Gale, who was an Australian 19th century amateur astronomer who was an observer of Mars and also did lots of good work on double stars. So Aussies are everywhere.
Oh, thank you so much for that. I didn't know that before. That's tremendous. I, of course, focused on the contribution that's been most closely related to our own work and to the Centre for Astrobiology, but I'm sure there are Australians that are involved at many different levels. So thanks for bringing that up.
Thanks, Tim. And thank you, Martin, once again. Before we close off for the morning, just an announcement for the next week. We're going to change direction, as is tradition here. We have Sherwin Morgan from Jord International, and he will give us a presentation on coarse and fine particle recovery in one device, NovaCell apparatus. Thank you so much. Join us live in the lecture theater next week. Thank you.